So, now let us look at the MOS capacitor, but start looking at the capacitance voltage characteristics of the MOS capacitor. The essential idea of this experiment is to see how does measure the capacitance of the small signal capacitance of the MOS capacitor, and see how the the capacitance varies when the VG or the gate voltage varies. So, we have already done these kind of exercises before. If you look at, if you remember the metal semiconductor junction, we built an equivalent circuit. We said that the metal semiconductor junction, it had a rectifying nature. If it was a Schottky junction, it had a depletion capacitance, etc. In the case of a diode, we said yes, in reverse bias it had a depletion capacitance, and in forward bias it had a depletion and diffusion capacitance. So, this is another such exercise, but with the metal oxide semiconductor capacitor. Okay, so, we have been calling it a capacitor. So, let us start measuring the capacitance. So, what is the capacitance of this capacitor? So, here is the experimental setup. Okay, so, how do you measure capacitance? In order to measure capacitance, essentially you need to give an AC signal and measure the current through the AC current due to this AC signal. So, because a capacitor would have an equivalent impedance of about 1 by j omega c. If c is the capacitance, the impedance is about 1 by j omega c, where omega is the frequency, which is angular frequency, which is 2 pi f, with f being the frequency in hertz, c being the capacitance, and j the complex number square root of minus 1. Okay. And if you apply a sinusoidal or a time varying voltage, it is only a time varying voltage that is going to create a current in the capacitor, and therefore, the time varying voltage is going to create a current of V by this impedance, which is going to be the voltage applied into j omega c. And by measuring this current and by knowing this voltage and knowing the frequency, you can extract the capacitance. So, there are many equipments or instruments that will measure the capacitance for you in a very accurate manner. And our investigation here is not the development of the instrumentation to measure the capacitance, but let us assume that we have an accurate estimate of the capacitance, and we are trying to see or guess what the capacitance will be based on our understanding of the MOS capacitor. So, this is our experimental setup. Okay. So, we have our gate voltage, but the gate voltage is now variable. Okay, and we can vary it from say a very negative voltage to a positive voltage. So, we have a variable gate voltage, and on top of this gate voltage, so we are going to apply a gate voltage, and on top of this gate voltage we are having a small signal, that is our capacitance measurement signal. Okay, that is applied, a small signal AC that is applied along the large signal gate voltage. The gate voltage determines the DC value and the small signal determines the AC value. Okay, so, it is an AC signal, and all operations are linearized around this AC measurement, right. And using these two in combination, we are going to estimate what the capacitance is. We are going to see what the behavior of the device is. But as before, what is small signal capacitance? So, let us say you have a device sitting in a black box, and let us say it has got 2 terminals outside. So, the way we want to define capacitance is we will apply this small signal fluctuation, voltage fluctuation, and we are going to estimate what the charge fluctuation because of this small signal is. Okay. So, how does the charge in the device under test respond to our small signal fluctuation? That is the measurement of the small signal capacitance. So, it is dq by d applied voltage. Okay. So, that is the small signal capacitance. Okay. So, that is, so we are going to, what we are going to do in this experiment is we are going to have this AC signal, we are going to set the frequency of the AC signal. Okay, we have a knob to set the frequency. The magnitude is typically kept very low, we will not worry about the magnitude of the AC signal, we will keep that constant, but we are very interested in the frequency of the AC signal, and we are interested in varying the gate voltage. and also the rate at which we vary the gate voltage, and I will let you know about that at some point. Okay. So, first let us say let us run our first experiment. Okay. So, let us not worry about the MOS capacitor to start with. Let us start with a very traditional metal insulator metal parallel plate capacitor that all of you are very familiar with. So, you have let us say we were trying to build the MOS capacitor, but we forgot to put the semiconductor. Okay. So, unfortunate, but we ended up with this structure here. So, you have the gate metal, you have the insulator, and you have another back contact. And the experiment we are going to run is we are going to vary the gate voltage, we are going to vary Vg from a very negative value through 0 to a very positive value, or let us say through flat band, but here flat band does not make any sense. So, from negative to 0 through positive value, and we are going to see what the capacitance per unit area is. What is the capacitance I am recording from this measurement? So, what do you expect for a metal insulator metal? So, let us say the thickness of the insulator is Tox and it has got a permittivity of epsilon ox. Okay. So, what is the capacitance per unit area of this capacitor? It is simply it is a parallel plate capacitor. So, therefore, it is epsilon ox by Tox. Okay. So, do we expect the epsilon ox by Tox to vary with the applied voltage? The answer is no, because the insulator is ideal, there are no trap charges in the insulator, and we do not expect any variation. Okay. So, therefore, the result that we expect to see is this. So, if you were to sweep Vg as you go from negative values to positive values, this capacitance will be constant ideally, and the value of this is going to be epsilon ox by Tox. So, that is the value it is going to take. Okay. Now, we can also try to vary the frequency of the AC signal, we can try to vary the speed at which we sweep, etc. But ideally, for an ideal capacitor, all this should not make any difference. You can measure the capacitance at any frequency and you should see the same behavior. But of course, in reality it is not going to be so, because every capacitor has also got a say a resistor in parallel, etc., etc. So, there are many leakage mechanisms, etc., which is not going to allow you to see this response. But let us just talk about the ideal case for now. Okay. So, now let us say we went back and we constructed our MOS capacitor more correctly. Okay. We now brought in our semiconductor and we are going to do the same experiment, but with the metal insulator semiconductor metal structure. So, what is going to happen? So, now as you vary the Vg, our semiconductor is going to react to it and the structure is going to behave very differently. And why is it different? So, let us say we are in accumulation mode, that is Vg is less than Vfb, we are in accumulation mode. And what happens in accumulation mode? All the majority carriers appear at the interface, and in this case the majority carriers are the holes, and you find that all the holes have appeared at the interface. The band bending is now like that, and you have all the holes appearing at the interface. So, for Vg less than Vfp, if I were to provide a small signal fluctuation, I have now set my gate DC voltage, right. So, let me pin my DC voltage first. So, we have now set Vg equal to Vg minus Vfp equal to minus 1 volt and left it there. Okay. So, our DC point is set, and now we are going to apply the small signal AC. Okay. So, I have forgotten to add the AC source everywhere. So, we apply the small signal AC and we are now going to measure the response of the carriers in the MOS capacitor. So, what is going to happen if the gate metal fluctuates a little? You will find that since there is a charge fluctuation on the gate, since the negative charge on the gate is fluctuating a little. So, you have some negative charge on the gate because of the DC voltage, but now because of the AC signal this negative charge is fluctuating. This small fluctuation has to be reflected by the whole population, and the holes are also, number of holes is also going to fluctuate in response to the fluctuation here. Okay. So, it is as though you now have a capacitor which is got a gate metal, you have your insulator, and this fluctuating hole population, there are plenty of holes in the semiconductor, there is no dearth of holes, it is a p type semiconductor, they are the majority carriers. This fluctuation of the holes is like equivalent to another metal plate if you imagine. So, you can imagine a metal plate, an imaginary metal plate here, and therefore, it is like you have carriers fluctuating, okay, if you want to imagine it that way. But more properly what we are looking at is the charge fluctuation in the device under test in response to the applied signal. And what is the charge response? It is the hole fluctuation in the semiconductor insulator interface. And therefore, our dq by d applied, the small signal applied voltage, is simply going to be, what is the hole population going to, what is the fluctuation there? It is simply Cox into Vox, right. So, Cox into V, so that is the voltage difference. And therefore, our capacitance is going to end up being just Cox. But now let us say we increase the gate voltage, we reach a point where Vg is greater than Vfb, but it is still less than Vt. We have still not reached threshold voltage, but we are greater than the flat band voltage. So, in this case the interface is now depleted. So, we are in the depletion mode of operation. So, what is this capacitor like? You can now imagine this back metal with an ohmic contact and this doped semiconductor with, which is basically like a resistor, okay, and you now have a gate metal here, and in between you have two capacitors sandwiched in series. You have the insulator capacitor and then you have the depletion capacitance, okay, and we all know how to calculate the depletion capacitance by solving Poisson's equation. So, this region is depleted, does not have free carriers, you can imagine it to be an insulator, another insulator, okay, if you wish. So, you have a series combination of these two insulators. So, the capacitance now decreases, it becomes a series combination of not only it is not only Cox, but it is a series combination of Cox and C depletion in depletion mode operation. So, that is the capacitance that you see. And if you want to imagine the response to the charge, how is the charge responding? So, let us say you have applied your AC signal, there is a small fluctuation on the gate, okay. So, we have now set Vg is equal to, is greater than Vfb, but it is less than Vt. So, let us say that is our Vt point, okay. So, that is Vt, and this we are plotting Vg minus Vfb. So, we are somewhere there, we are just slightly above Vfb. So, we have depleted the semiconductor and now you are fluctuating this voltage. So, there is a fluctuation in this voltage, right. So, we are moving this voltage back and forth with our small signal AC. So, how does the semiconductor respond? It responds by increasing or decreasing the depletion width. So, the XD increases or decreases in response to the applied voltage, and by increasing or decreasing the depletion width you are either covering or uncovering all the fixed ions. So, if the depletion boundary is there, you have uncovered all these, and if the voltage on the gate increases a little, you need to add more negative charge, and therefore, that goes away and the XD increases a little bit more, you have more negative charge being uncovered, okay. So, that is the response of the semiconductor to the applied AC signal in depletion mode operation, and therefore, it is a series combination of Cox and C depletion. Okay. And what about the inversion mode? Inversion mode operation. So, if my Vg becomes greater than Vt, okay, greater than or equal to Vt, you have a lot of electrons in the interface, okay. So, electrons have appeared at the interface. So, I have still shown the depletion region here, but the electrons are now sitting there, they are probably I should have redrawn this picture, but this picture is not entirely accurate because you can still see the depletion region. The depletion region does exist, but I am worried about the way I have located the electrons. See, these electrons must be located at the semiconductor insulator interface. So, the electrons are located there, not on the other side of the depletion region. Okay, so, this is a mistake. So, I apologize, and it is a mistake. So, it is actually quite a serious mistake, I would say, because it changes the situation a bit. So, the electrons are at the semiconductor insulator interface. You still do have depletion regions, but the electrons are between the depletion region and the insulator. Okay, so, they are at the interface. Okay, so, please do make this correction here. And since the electrons are at the interface, any increase in any fluctuation of charge for Vg greater than Vt. So, we are now operating there. So, we have crossed Vt, we are now operating here, and any fluctuation in the gate voltage is going to respond to the electron population increasing or decreasing. Okay. So, this situation is exactly like if you think of it as if you want to imagine things as a metal insulator metal plate, this electron sheet is acting like your pseudo metal plate. Okay. So, it is like exactly like what the holes were doing, the electrons are doing the same thing now. Or in other words, all the response to the applied charge on the gate is being met by the fluctuation in the electron charge at the semiconductor insulator interface. The depletion width need not increase or decrease anymore. So, the depletion width is more or less static now. So, that is not the response anymore. Okay. So, here it was the depletion width that was responding, here it is not, here it is the electron count that is responding, and therefore, our capacitance once again becomes same as Cox. Okay. So, the capacitance is Cox, then it decreases, then it again increases and comes back to Cox. But this is all under a specific condition, and we will explain that condition soon. Yeah, and the condition has got to do with the frequency of the AC signal that we are using to make this measurement. Okay. So, here in the accumulation mode we had holes appearing at the interface, and there are plenty of holes in the semiconductor, absolutely no problem, you have enough holes present for you for them to respond to your applied gate voltage. In the depletion mode, if the frequency changes, the frequency of AC signal changes, will the covering and uncovering of the ions respond to an increase in frequency? The answer is yes, because it is a response of an electric field, right. It is the electric field, whether the bands are bending fast enough. So, of course, they can respond. What about the appearance of electrons, the minority carriers at the interface? So, these electrons are very few in the bulk material. So, where are these electrons coming from? These electrons are coming from these are thermally generated electrons in the depletion region. They are thermally generated. There is a certain rate of thermal generation. Okay. So, there is a certain rate at which they are being generated, and if the AC signal frequency is much higher than this rate, then the electrons cannot respond to that AC signal frequency. And if the AC signal frequency is much lower than this rate, then no problem, the electrons will respond in the manner which we described. Okay. Therefore, the signal frequency becomes very important when we look at the response, the capacitance of the MOS capacitor in inversion mode, when the minority carriers come into the interface.